Yo, yo, yo. What's up, what's up? Welcome back. Today we're working on my operating system, currently titled Stream OS because I'm making an operating system on Stream. And what we want to look at today is we're like upgrading our boot process. So a little background, we have an x86 operating system. It has like boots, it has memory allocation, has like concurrency with a cooperative concurrency. It does serial, has a clock, unit test, has like an Ethernet stack, web stack, whatever. We've proven that we can run like a web server on and stuff, and we have like a little bit of a game. Like this little dummy game just to prove that we can. So where are we here? Where we just have this like little dummy game, little brick breaker, just to prove that we can like read and write the screen. Great. This is all running in like a QEMU virtual machine. And the idea is that like we're kind of like trying to learn about how operating systems work and maybe eventually gain like a better understanding of what happens when you run like normal user space code on a normal operating system. And you know, maybe we get to the point where this boots on real hardware someday. I don't know. There's no real like goal in mind. We're just kind of like playing around, learning, etc. So what we've been kind of working on recently is working towards like multi-core support. So right now everything's running on one CPU, but it'd be nice if we could run on multiple. And so there's kind of like a bit of a rabbit hole to go down. We've kind of been recently working on like preparing our system to support multiple threads. So we've been upgrading our mutexes to use like atomic variables. We've been upgrading our like static variables to be thread safe. We've upgraded our executors to support like work distribution across threads, but we haven't actually enabled the CPUs yet. And so what I was doing is I was like reading about like symmetric multiprocessing, which I'm pretty sure is the model that most x86 machines use. I think that more recently I've seen kind of an uptick in asymmetric multi-core systems. Like I know the latest MacBook has like high priority and low priority, or like high power and low power cores. I'm not sure if the latest x86 ones or x64 ones are the same. But anyways, I think under this model, we can use symmetric multiprocessing. And when I was looking at like how do you initialize this stuff, they use this thing called like the Advanced Programmable Interrupt Controller, APIC, Advanced Programmable Interrupt Controller, which is like a more beefy version of the interrupt control that we're using right now that supports multi-core. So that means before we get to multi-core, we have to enable this thing. And in order to enable this thing, we need to find where they are by parsing this like MADT, multiple APIC description table, which is an ACPI table. And it's like, well, how do you get ACPI? Well, it's like, well, to get ACPI, you must look for this RSDP, root system descriptor pointer. And so you go to this page, and it's like, hey, how do you find this thing? Well, like maybe you look through like BIOS memory, read-only memory, look through like the first little bit of your normal memory space, or maybe like in UEFI and BIOS it's different. Or if you're using a multi-boot 2 compliant bootloader, you can look for it in the ACPI tag. So then if I go look at like multi-boot 2, in here, one of the things that like the bootloader will hand off to you is in fact the let's see, ACPI. They'll like give you a copy of the descriptor table. Great. So it looks like in order to load the ACPI table so that I can find how my advanced programmable intercontroller, so I can initialize them so that I can boot my multiple cores, I should enable multiboot 2, which is this like specification from GNU, I don't know, I think they say the G, I can't remember, that basically just describes how you should boot an operating system. And it looks like this is like from 1995. I currently have like a multiboot 1 implementation, which is also from 1995. That's pretty funny. So these guys are just like in the same year. What the fuck? Or maybe multiboot 2 is 2016. This is the only one. I don't know. Not sure. But it looks like, yeah, that's what I want to accomplish today, is like figure out how to boot with multiboot 2, make sure that we stay like compatible with all of like our existing features. So like right now we get the frame buffer so that we can draw graphics through multiboot. We get like our memory space through multiboot. And so we want to like boot with multiboot 2 and parse the table to the point where we can do all of the things that we were doing before. Great. Yeah, so that's what we want to get done today. So the first thing to do is probably start trying to update our definition of what we tell the bootloader we support. So right now, what we do is in our in our boot file, we can just declare a like multiboot section. And in here, we provide this like magic number that says like, hey, we're a multiboot header. We give it some flags and a checksum. And then we like ask for some frame buffer stuff. It looks like the multiboot 2 stuff is similar but different. We have the magic architecture now. So that's different. That's new. Header length and checksum. And so let's look at what these guys say. The field magic is the magic number identifying the header, which must be the hexadecimal decimal value, this guy. Okay, so we'll just kind of huck this in here. So I'll replace the magic with this. The field architecture specifies the CPU instruction set architecture. Since magic isn't a palindrome, it already specifies the endianness ISAs differing only in endianness receive the same ID. 0 means 32-bit protected mode I386, 4 means 32-bit MIPS. What are the other values? Like, hello? They only have 2 values? Okay, sure. So here, we'll say architecture is 0. We'll say I386. So here, we stick in the architecture. Great. What's next? What is next? Where the architecture is also with U32. Header length is the length of the multiboot header in bytes, including magic fields. Is that supposed to be... oh, I see. That's with all the tags. So we don't know this yet. But let's just say this is with the magic. So this is... we'll start with 12. 16. 0, 4, 8... 0, 4, 8, 12 to 16, yeah. So we'll stick 16 in here for now. And the checksum is a 32 unsigned value, which when added with the other magic fields, i.e. magic, must have a 32 unassigned sum of 0. Oh, I see. So we add up, what? It's like 0 minus magic minus architecture minus size. Architecture minus size. I don't know if this will do the right thing, but we will see. So I guess let's start by booting with this and seeing what happens. Presumably, this is going to be a problem. So here we'll say set size is equal to 16, and here we'll use size here. Great. Let's see what happens if we try to build this. Presumably our OS doesn't boot right, so he doesn't like that I didn't put a comma here. Architecture cannot be, so I think I probably spelled architecture wrong somewhere. Yeah, architecture, there we go. Out of range of literal value, so this should probably be 1 to 32 minus 1 or something. No, how do you do this? Yeah, 1 shifted left by 32 minus 1. Okay, no multiboot header found. Okay, so that's interesting. Let's look at this again. No multiboot header found. Oh, maybe I have to say somewhere that multiboot 2, maybe? Cargo build Let's see, the multiboot to grub. Let's see if there's like a way to ask it. Here we go. Perfect. So let's see if this guy has it. So we'll look at target release. No, it's target release kernel, and he doesn't find it. So, aha, GNU LD has a default page size of this for ELF64, which will fail the multiboot 2 size test. Why? Why? Hey yo, what's up? Why does page size matter here? That's confusing. I would think that I'm not paging at all, so I would think that the page doesn't matter. But let's see. GNU Grub is compatible with multiboot 2 spec as of version 2.02. Why does page size matter where? Here they're saying that GNU LD has a default page size of this for ELF64, which will fail the multiboot 2 test, but I don't understand why page size is relevant in like my binary data. But let's come back to that and see if I've got my other stuff right. So I should have magic, which is E85250D6. Multiboot might set up some pages for you. Sure, but like I might be confused about how like the linker is specifying page sizes at all. I would think that like the linker generates like a flat binary and like paging happens underneath that level if I understood correctly, which I clearly don't. But my understanding was like I stick my kernel at like this address in memory, just like 0x8000000 something, and then when I access that memory, if I'm paging, then like that would be mapped from virtual to physical memory in some way. But I just didn't think that like paging was relevant in like the binary itself. But I must be missing something. Okay. Cargo build release. I assume all dynamic objects must be aligned on page boundaries, otherwise load and unload errors might happen. That seems like possible. That doesn't shock me. That wouldn't shock me if that was true. Okay. So grub file. Let's see if is multiboot at all. No. If I undo all the changes I made here and build again, do I see the multiboot 1 header if I look at the debug build that I just made? No. Okay. So I'm misunderstanding how this grub file thing works. Oh, it has an exit code associated with it. Aha. Okay. So grub file is x86 multiboot 2. This returns 1. Great. Build again. And here it says 1 again. So let's try throwing this like max page size equals size in the middle of my linker command just to see if that's like related. There's also a good chance that I fucked this up. If like if I need to have like tags at all, maybe I need to like maybe if I don't terminate my tags, then there's a mistake in here. So let's try that. Tags constitute a buffer of structures, blah, blah, blah. Tags are terminated by a tag of type 0 and size 8. So let's do that. So we have short 0, short 0, long 8. So this is a terminator tag. Size now should be 24. And let's look at the cargo build. Let's maybe hex dump the kernel I just built and see if I can find, oh my gosh. Let's open it in like a GUI hex dumper. And I wanted to see if I can find the multi-boot header in the binary I just built. And then I can like kind of like double check it manually. Oops. Okay, so if let's look at what I wrote in my linker script. I think in here, I stick the multi-boot header at around 1 meg in. Right, so there's all these 0 padding for 1 meg. Blah, blah, blah. And then here, somewhere around here, I should start seeing the multi-boot shit. So what is the header here? E85225D6. So can we look for that? Search for E85250D6. We didn't find it at all, but maybe because the endianness is backwards. So we need to actually look in little endian order. So D6, 50, 52, E8. And we do find that here. We say 32 bits of 0 for an architecture 86. And then our checksum here is, sorry, so this is the multi-boot header here, I think. Yeah, here. E85250D6. Then I have 0000. And here I have 18 for my size, which looks wrong. Oh, hex 18, which is correct. Which is 24 decimal. And I think that's right. So this is 4, 8, 12. Hey, are you, Mr. Start of Stream, are you trying to use QEMU with the kernel parameter? No, I'm booting with grub. Yeah, I'm booting with grub. But grub is saying that it can't find the multi-boot header, so I'm just double checking that I haven't done something stupid. Okay, and then my checksum is this, and I guess what we should do is double check that that's correct if we manually try to validate it. So here they say the checksum is a 32-bit unsigned value which when added with the other magic fields, magic architecture and header length, must leave a 32-bit unsigned sum of 0. Okay, so let's double check that. If here, I guess if I just open up like a Python, let's do this. Python 3, and we'll punch in this number. So this is 17AD AF11 because you need to invert it because it's a little endian. And then we'll just add in the other thing. So we need to add in the header of 0x18. And what the heck? Oh, it's frozen. Shit, that's annoying. 1, 2, 3, 4 plus 0 plus the magic. So E85250D6. E85250D6. And I want to print that as hex, so I guess we say print. I think I do like format as hex, and then this. I'm off by 1, so it's probably this -1 is like an incorrect checksum because it's supposed to be 0, not 1, 1, 1, 1, 1, 1, 1. Okay. Let's build this again and check if we see that. And there we go. Now we're exiting 0. So we were off by 1 on our checksum, and that's probably why grub was refusing to boot us. So let's see now if we run. Does grub think that we are a bootable OS? Yes. So it says it's booting. Now nothing is happening, probably because I'm parsing this multiboot 2 header as a multiboot 1 header, and that's just like fucking shit up, would be my guess. So maybe what we can do is we can launch with grub, or not grub, sorry, GDB, cargo run. We say GDB, I think it's GDB equals 1 cargo run is our like script parameter to like launch with GDB enabled. So hopefully now we should see guest not initialized. Great. And now I should be able to open up like a second window. And if I connect GDB, I think that I should be able to at least see the entry point. So I think I have a script here somewhere, run.gdb, and here let's just like break on a async main, or kernel main, I think is what it's called. We'll just set that up by default so I don't have to like type it anymore, and then gdb-x run.gdb. And we see no breakpoints, which is not good. And we might never see our kernel get loaded, which is interesting. Interesting for sure. Let's see if we're doing anything in our like boot.s or like our initial boot up sequence that has anything to do with multiboot info. It looks like we don't do a lot. We just like set up a stack and call kernel main. So maybe I wonder if we can like somehow signal to ourselves that we got to main. How do we want to do this? If I remember correctly, we could just try to shut down the operating system immediately using this like exit port. So let's kind of just pull out this stuff. Oh, that requires allocating. Shit. So I guess we can just write a number here. We'll just do like some like raw assembly. So car arch ASM. And we can just write to this like QEMU exit port and try to see like an immediate crash. So this is, we gotta like kind of dig under the hood a little bit. So we have like these like IO allocator things, which is like an abstraction around this very simple assembly call, which is just out. Here we go. So here we'll just copy this stuff in here. Like this. And we're missing, our brackets aren't matched up correctly for some reason. Here we go. There we go. And here we just need to set our address to this. And the value, we'll just set like, we'll write like a 1 for now. And let's just see if this does anything. If this works correctly, we should see an immediate exit. This doesn't compile because we have to make a return here. Let's run without GDB for a second, just to see if we're actually getting to this point. Oh, okay, so that's good. And what happens if I write like 11? Do I see a different number come out? Yeah, okay, so that's a good sign. We're definitely getting to the point where our kernel boots. And it's more like for some reason GDB wasn't hitting that breakpoint. So I wonder if we can get to that somehow. So let's look at our GDB run script and let's try breaking at this specific line with GDB equals 1. And let's look at our GDB run script. And probably the problem is that I was looking at the release kernel instead of the debug kernel. So that's a pretty obvious reason that this wouldn't work. There we go. Okay. So we're now like hitting our breakpoint, and now we can start like inspecting what we're getting from the multiboot response now. So let's look at what they say. What should we be getting from them? So EAX must contain the magic value of this guy. So we should see, if I remember correctly, our boot script, it should propagate the correct registers. So let's just double check. So we put EAX on the stack last and EBX on the stack second last. So one of these guys should hold the magic value. So let's look at multiboot magic. And can I print it as hex? That looks a lot like this number, 0x36D76289, and this says 0x36D76289. So we're on like a really good track here. We've booted with multiboot 2, and we are receiving the info back from the operating system that we're multiboot 2. And we're in GDB, so we can like debug that we are at least we can start like poking the memory, and like without printf and stuff being up, we can still start seeing feedback. So that's good. So here we'll say booted with multiboot 2, and we're at what, like 25:55 in a stream. And what are we doing next? Parse multiboot 2 info. That's the next step. So let's see, what do they give us? So we should be having in our info, I think you can say, I think I can say info as constuate. And then I think that there's a way to like print 10 of these guys if I say like star and add. There we go. Yeah. So let's just like look at the memory here. What do we see? Upon entry to the operating system, it contains the physical address of a multi-boot 2 information data structure, through which the bootloader communicates vital information to the operating system. Great. So what is like the... So sure, they're telling us tags. The boot information consists of a fixed part and a series of tags. It starts 8 byte line. Fixed part is as following: total, size, and reserved. And every tag begins the following fields: type and size. Okay, so I guess the first thing we should do is see if total size makes sense. So this is, and this must always be 0. So total size is U32, so that's these 4 bytes. Great. And the second 4 bytes should be 0, so that's lining up, right? We're seeing a 0 here, and we're seeing that we have 0x430, which is just over 1,000 bytes. And what do we see? Every tag begins the following fields: a U32 of type and a U32 of size. So after these 4 zeros, we have type 15 and size C, which is 12 or 13. Okay, so what is type 15? Which I guess in decimal is 21. So I guess we can look for type equals 21. And okay, so we're seeing like the image load base physical address. It is provided only if the image has relocatable header tag. I don't want my image to have the relocatable header tag. I don't want that at all. In fact, I should have no tags. So that's a little odd. But that's okay. Size 12, does that line up? I think we had 0xc, and that is 12. Okay, so at least that's lining up. And I guess what we should do is we can make like a iterator that iterates over these multi-boot segments. And for types that we care about, we'll like map them into specific structures. And for types that we don't care about, we'll just skip them. That seems pretty reasonable. So I think I'm okay to like just start implementing that. It looks like we've like got something that looks kind of reasonable. So I guess here we'll go into the multi-boot section, and maybe we'll make a new multi-boot 2 module. That seems reasonable. Because I think that they're pretty distinct. And in here, let's just start. We'll make a function like parse multi-boot info. And he'll eventually return something, but for now, we'll probably just, well, I guess, we'll figure it out later. And what's he gonna do? He's gonna take in the magic. which is a U32. And what else is he going to do? He's going to take in a info, which is a U8 pointer for now. And what do we do with this guy? We convert him into like the multiboot header. We first need to parse this guy, so we're going to say that this is probably actually the multiboot boot info. What do they call it? Fixed part. We'll just call it the header. And in here, he has a type and a size, or a total size and reserved. So total size is U32, and reserved is also U32. And now what are we going to do? We're going to say, first we're going to check the magic. So we're going to say assert EQ magic. And wherever they said the magic is. Where did we get that number from? Here we go. EAX, magic value, this guy. Great. And the info is then going to be a pointer to boot info header, but I guess we'll cast it here. So we'll say, let info is equal to info as const boot info header. And I think we probably need to repr C here just to like make sure that it doesn't fuck around with our struct layout so that we get what we expect. And I think that like usually I'll write packed here, but I think that you don't have to write packed if the alignment line works out correctly, which I think it will here. We'll see. And I think that kind of makes things easier. Okay. So from the info, we're gonna want to be able to like get the get an iterator to the tags. So we probably have like how do we want to do this? Let's just start typing and see what happens. So we have this guy, and he has a function that's like tags, right? And he returns some sort of like iterator where the item is a tag, which is unimplemented, and we need to say what the fuck is a tag now? Maybe tag is the wrong word. Let's see what they call them. Totals. Every tag begins with the following fields. Okay, they call them tags, and I guess each tag will have like his like type. So let's start with the one that we know we have. We have this like image load base physical address, and I guess each one of these guys will contain his like address. Maybe. I guess he's gonna be a pointer to a structure. And then if we just punch in the like what we expect the structure to look like, maybe we just get some stuff for free. So let's try that. Let's derive debug for this image load guy. And let's see, what does he look like? He has a type. He has a size. And then he has a load base adder. Okay. And so then what's our iterator going to look like? We're going to like start from the address of myself. So we're going to say let header is equal to, I guess, header address is equal to self as a pointer to boot info header. We'll say that the first tag is equal to header adder add 1, right? So we're going to skip over the header at the header. And then we need to like create an iterator over tags. So this is probably going to be like a type here. He's going to have like his end address. We probably are going to want to store that so that we know when to stop iterating. Theoretically, we could stop when we see the like the stop tag. But we probably also want to double check that we're not going over the ed. We're going to say what our location is a pointer, just like a normal const-u8. And the end is going to be also a const-u8. And Rust has like these like iterators. So I can probably just say impl iterator for tag iterator. And I can just start shoving in the stuff that we have to implement. And this is actually a pretty simple interface. Sweet. So our item is going to be tag, right? And so we're going to match. So I guess we say if self dot location is equals self dot end, return none, right? There's nothing more to do. And if self otherwise, we look at the type of where we're iterating at. So each tag starts with a type and a size. So we're going to say let type is equal to the location of our iterator as a U32. And the size equal to self.location add 4 as U32. And I think we can just dereference these. Okay, so we have the type and the size. So then maybe what we can do here is instead of including the type and the size in each of these guys, we'll kind of like assume that those have been handled by the iterator. And we'll say let item is self.lock add 8 as, and we don't know what we're going to cast this to, so we'll leave this as a U8 for now. We're going to look at the type. And if we have 21, we're going to convert this into an image load. Like this. Otherwise, we continue. So here we're going to put this as an infinite loop, actually, because if we have an unhandled type, we just want to continue. But we also, let's see, here we'll return, no. So unconditionally, we're going to set self.look is going to be plus equals to size. Equals self.look.add size, right? And then I think that here we can just say, if we have a tag we recognize, we return some of this. Otherwise, we do nothing and continue. And I guess we don't even have to continue because the loop will automatically continue after this, so we can just do nothing. We need to cast this to a usize. We delete this to do. If we hit the end, we break. And if the type is 0, we also return none. Okay. So that should be enough for us to start like iterating over tags, and then all we have to do is start like implementing each of these guys as we come. But let's first see. Let's see if we actually get what we want here. So let's see, how does that work? So here we find we get the header address. We can get the size. So here we have the boot info header. Great. So we can say header adder. Oh, we have to construct the tag iterator here. Right. So what's in the tag header? iterator. We need the end. So let end is equal to header adder. Let's see. End is equal to the header adder as a const u8, so that we're doing the math in bytes. And we're going to add in the header pointer total size. Okay, so we've got the end. And our first location is going to be the location of the first tag. So this is going to be header adder add 1 as const u8. And then we can just construct our tag iterator. So this is look and end. And that might be it. So let's now do like a for tag in tags. Oops, this should be info tags. Like this. And let's just, if we do nothing here, will Rust optimize out our loop? I guess maybe we'll like print line tag, even though our print line stuff isn't up yet. That's okay. And I guess maybe it's actually kind of nicer if instead of a pointer here, we just get a reference. Right, so we can do this actually. So here, I think I dereference our pointer and then get the reference to it by just doing like a little one of these guys. Cool. And now here, instead of doing this immediate quick, we can do multiboot to parse. Oops. This guy needs to be public. Multiboot info. And we pass in the multiboot magic and the info. We'll convert this to a const u8, and this guy will be like this. Okay, so now I think we can look at our GDB script, and we want to change our breakpoint to here. Oopsies. Oh, shit, my whole computer crashed. Oh, are we back? We're back. We're back. Okay. So here we want to break on bit. Oops. What's happening? I think I had caps lock on by mistake. There we go. So we break here. Okay. So cargo run. And here we run our GDB script. And let's look at the tag. Okay, so we have an image load tag. That's very good. That means that our like parsing logic saw at least what we expected to see. And let's double check that we're seeing the image load structure that we expected to see. So can I somehow get this value out? How do I, oh, here we go. Yeah. Dereference tag 0. And so I have a load base address of this guy. Can I print with hex? Okay. Wait, that's looking like something reasonable. If we look at our, let's see, if we look at our, ooh, we can compare this to the kernel start value. Yeah. Great, no symbol kernel start in the current context. Cool, that's what I wanted. But I think we can check, I guess the kernel start value should just be in our linker script. Wait, is this... What's happening here? Yeah, so I think if in our linker script, we say that we want to start at 1 megabyte, our kernel start should be at 1 megabyte, and I'm pretty sure that this is 1 meg. 1, 2, 3, 1, 2, 3, 1, 2, 3. What is this? Print this number. 1, 2, 3, 4, 5, 6. Yeah, that's 1 million in. Yeah, okay, very cool. Very, very cool. Okay, so that's sweet. So we've parsed a tag from the multiboot header. And now I guess what we need to start doing is parsing all of the tags we like. So, what do we care about? EFI, EFI, EFI. We're not using EFI right now, so we don't really care. Network information, we don't really care. ACPI, we are going to care about later. But I'm not going to handle that right now because we're trying to get feature parity before adding on the other stuff. Frame buffer stuff, we're definitely going to care about. Because we use this all right now in our multiboot 1 implementation. But here, this is what I really want to know. I want to look at the memory map. Because the memory map lets us initialize our memory allocator, and that lets us boot the rest of our operating system, basically. So let's look at type 6. And we're going to return a memory map type. So here we just go like this, and we replace image load with memory map. And we have a very length entries section. So we have type 6 size, entry size, and entry version. So it contains the size of 1 entry, so in the future new fields may be added to it, guaranteed to be a multiple of 8. Okay. Future versions are guaranteed to be backwards compatible with the old format. Okay. Entry version is currently set at 0. Okay. And each entry has the following structure. He has a base address, a length, a type, and reserved. Size contains the size of the current entry, including this field itself, maybe bigger than 24 bytes, blah, blah, blah. What is guaranteed to be base adder is the starting physical address, length is the size of the memory region in bytes, type is the variety of address range represented, where the value of 1 indicates available RAM, blah, blah, blah. And then there's reserved. So really all we care about is we're going to pull out each of these base adders and lengths, and hopefully we find one that matches like what we had in our other one. So maybe we just print them all out for now. Okay, so struct memory map. So we know he has a entry size as U32. He has an entry version as U32. He has entries after that. So here we're going to have like a function to get the entries. And I don't know if Rust has like dynamic arrays or like, sorry, like dynamically sized structs. Probably not. Those don't seem very Rust-like. Like in C, you can do this like bullshit where you say like, extra shit is like a empty array. And then you can like just start indexing this array, and you get like kind of variable sized things by like mallocing areas of RAM, and then just kind of like indexing it like you know. Rust does have unsized structs for rep C structs. Oh, very nice. That is actually exactly what I was talking about. Rust unsized struct. Repr C. Oh. So you can just stick an array at the end and say it's an unknown size of entry. That's kind of cool. That's kind of cool. So you're saying that I can say entries is a thing of memory map entry. And here I say recurc and derive debug. Probably the debug implementation. I don't know if it'll let me. Yeah, because memory map entry. Oh, no, I was going to say because the entries is unsized, but maybe if we say recurc struct memory map entry, he also has to drive debug. I'm surprised this works. That's surprising to me. Cannot find type tag. Yeah, where did it go? What the fuck? I must have accidentally deleted it at some point. Here we go. I guess I accidentally nuked it when I was making my memory map. Okay. So let's see. Our entries. How do I know when the entry list ends? Entry size will contain the size of one entry. Cool. So is it like a 0 length is the last one? Blah blah blah. 3 where value of 1 indicates available RAM, 3 indicates unusable memory or usable memory holding ACPI info, 4 indicates reserved memory, 5 blah blah blah. 0 reserved sets a 0. The tag view. How do I know? Oh, because the size, the total size of the tag is set back here. I see. So I guess omitting the size info from these structs is actually not going to work. Okay. That's annoying. That's annoying. So here somewhere in my image load one, I actually do have to contain type u32 and size u32. That's fine, whatever. And then when I just don't do this for item. Here, we'll just do item is equal to self.log before we add. All right. And so that means all of these guys just have to have type and size at the beginning of them. Okay. So this guy returns a memory map iterator. Do I need to make like a specific type for this? Or can I return... I can just convert this into a slice, I guess. Why does this compile? I don't understand. I must not understand how to use unsized arrays. Here we go. So someone is saying dynamically sized types. I don't understand how he knows the length. External types with an unknown size. There's a good chance that this is just won't work the way I expect. Recurc unsized array rust. Blah blah. Somebody's got to talk about the like array at the end. Well, maybe not. I guess we can just try seeing what happens. So maybe I say like self.entries. I guess I'll convert it to a pointer for now. And then maybe we convert it back to a slice. We can say like core slice from raw parts, and we take in this we can calculate the size after. Why is this a non-primitive cast? Cannot cast a thin pointer star conjugate to a fat pointer star const memory map. Oh, that's down below. Okay. There's something I don't understand about these. Maybe it's probably easier for me to start with just saying that like we'll omit the thing at the end. Maybe I make it like a 0 size thing here, and that will give me the address of it. Oh wait, maybe I just have to put a little ampersand here. Okay, yeah, we'll say it's a 0 size type. We'll convert this to a const this. And then we can convert it to a const memory map entry like this. Perfect. And then we can convert that to the slice. So we can say let entries is equal to core slice from raw parts entries and self.size minus 8, no, minus 4, 8, 12, 16 divided by the length of the size of the entry. So it's core mem size of memory map entry. Okay, there we go. And this guy has to be a U size. Called on safe. And so now I can return that just directly. Which means that we need to return from our entries a like slice of memory map entry. There we go. Okay, so now what goes in this guy? What goes in him? U64. A length that's also U64. A type, which is a U32, and reserved is a U32. And now we look at the... depending on which tag we get, if we get the map, we're going to iterate over the entries. And here we'll print line the entry. And even that won't print, we can look at the debugger and that'll give us some sort of info. And for any other tag, we just continue. Let's cargo check. Cargo run. Which is going to... oh, oops. We want to run this in GDB. And let's look at our GDB script. We want to break here now. Okay, so we cargo run with GDB and we run our script. And weirdly, it's not doing anything. So where did we panic? Okay, so it didn't like something here. So we're parsing the multiboot info, and it panicked at self.lock as const u32. Why doesn't it like this? Why would I ever panic at this? Misaligned pointer dereference. Fuck. I see. So why would that be? Misaligned pointer dereference. So if we look at the multiboot 2 stuff, our size interesting. So I guess if our size isn't a multiple of 8, we'd have a problem. So here we can probably assert what size percent 4 is equal to 0. And this will tell us now if we get a misaligned pointer why that's the case. And yeah, I think that's fine. It's also possible that we've gone past the end. But let's try this for now and see where we get from there. Okay, so here we're in our panic. Here we have a size that's not 4. We have a size of 1, which is just like fucking invalid, right? Because I think somewhere here it says that our size needs the size of the tag, including header fields, but not including padding. That's so fucking stupid. Oh my lord. Okay. Fine. Okay, so 8 byte aligned. So we declare this as mutable, and size is plus equal to 8 minus size percent 8. All right. Let's go again. Okay, so we now have for entry and M entries. So what is our entry here? We do have a base adder here, 0, length of this. Okay, so we are getting entries that maybe look somewhat sane. This is probably our big ass one. 70 EO, which is what? This is 1, 2, 3, 4, 5, 6, 7, 8, 9. That's really big. This does look very familiar, though. This is looking a lot like, yeah, cool. So we did iterate over entries that looked like a certain sane size. And let's just double check. I think that you can set the size of the, of your QEMU memory. And I think that if we set it to like 512 megs and we see that that big one pop up to around 512 megs, we can be pretty confident that we're parsing this correctly. So let's try this again. So quit, and we run GDB with our scripts. And we're looking for a big chunk of memory. Okay, here we go. That looks like around 512 meg, right? If we print this, do we log to this? No, we divide by 1024 by 1024. That's what we want. So 510 megabytes, but there's 512 and there's like 2 megabytes approximately for something else. So I think that's like, that gives me like some confidence that this memory map entry stuff is like correct, which is pretty sick. So let's keep going. So what else do we need from this multiboot stuff? We definitely need the frame buffer as well. That's the other piece we need. Let's look at the multiboot 1 API that we've implemented. And we have get mmap adders and get frame buffer info. Great. So that's the only thing that we need to add to this. So it looks like what we did here was we created like a multi-boot struct where we could just pull the stuff out directly. We can probably do that again, and we'll just like iterate over the tags until we find the tag that we want, and that's fine. We don't have to like worry about like a little bit of extra iteration at the beginning. So let's kind of match that API here on the multi-boot 2 side. Okay. So let's start with making a multi-boot 2 structure. He's public. He has a function new that takes in the magic and the info and returns multi-boot 2. I don't know why my syntax highlighting is fucked. Oh, because it's inside the struct. So this should be impl multi-boot 2 like this. I think something just crashed. I'm just going to restart my language server / editor real quick. And here we're going to do some of the same stuff here. So our info, we're going to have this guy here. And I think that's all we have to do in our menu function is we construct our, we like get the header and we say multi-boot 2 info. Okay. Now, if we wanted to match the multi-boot 1 API, we have this function get mmap adders. And here he returns multi-boot mmap entries. Which means that we iterate over our tags. So this is self.info tags. When we find the memory map, we return it. So here we return m entries. Otherwise, we say panic, failed to find mmap entries. Cool. So I think that actually probably gets us into a pretty good spot where we can start trying to initialize the rest of our OS. And just for just to make things easier, I'm just going to make these entries map to the same name. So this is adder, this is len, this is type, and reserved. So I think probably nobody uses the size here, but they do probably use the length. Cool. Cool. And now here in main, I can say, what did I do before? I initialized my kernel with the info, and now I want to pass in the magic as well. Here, this is a const u8 now. And here we pass in the magic and the info. Here we pass in the magic as a u32 and the info as a const u8. And here we initialize the allocator with the multi-boot magic and the info. Which means in our allocator, we now take in the multi-boot magic and the info as a const u8. Our big block is going to be, instead of this, we're going to say let multi-boot info, or we'll just reassign it. So say let info is equal to multi-boot to new from the magic and the info. And I think the rest just works. We just have to disable the frame buffer. for now. So let's just remove everything that uses the frame buffer. And we're pretty close now. We just have to run the rest of this stuff. Okay. We have some like permissions shit going on, so this needs to be a public struct. It looks like we're running now. And let's see if I like run my unit tests. Nothing. Hey! That's pretty sick. Okay. That's really sick. Okay, so we've gotten everything but the frame buffer up. So, right, because we can tell that we've like initialized our kernel. All of our unit tests are passing. And I'll bet you if I run my kernel, I won't get my... see, I'm not getting like the graphics stuff initialized, but I am getting like all of my logs here. And if I try to talk to it, I think it's like this. TCP is working correctly. Yeah, I think overall we're up and running other than frame buffer. So let's say boot without frame buffer. And that's at an hour and 11 minutes and 28 seconds in stream. We'll just say 30. And so now we'll just say initialize frame buffer. That's pretty sick. That is pretty sick. I think this is probably worth checkpointing. So we'll just say checkpoint. We'll check a new branch. We'll call this what, multiboot 2. And we'll say we're checkpointing multiboot 2 boots without frame buffer. All right, very nice, very nice. Yeah, and I guess all that's left is to pull the frame buffer stuff out. So, so here's a if let. We'll just quickly get rid of this annoying log that says he wants us to use if let, because that's like, you know, arguably nicer. I don't know if it really matters, but the linter prefers it. And now we'll just do the same thing for frame buffer. So I guess we have to make a function that's called get frame buffer info. And he's to return a frame buffer info. Let's try to keep this frame buffer info struct compatible with the old one. So we'll just copy paste it, because we're going to delete the old multiboot stuff later anyways. Instead of trying to like maintain both multiboot 1 and multiboot 2 support, we're just going to nuke multiboot 1 once we're done here. We are going to look at the, oh my gosh, why is this opening new windows instead of opening the ones I already have? Hello? Let's just press every single button on my keyboard to make sure that there's like, yeah, okay, Kwin thought that like a modifier key was stuck down. That's fucking annoying. Oopsies, I just gonna pin something. I didn't mean to pin your message. How do I undo this? Unpin. There we go. Okay. So where were we? We're trying to go back to this multiboot 2 stuff, and now we want to parse the frame buffer info, which we saw here somewhere. Here. I guess we don't just need to parse it though, we need to request it, right? Because when we were working with multiboot 1, we specifically asked for 640 by 480 640 by 480 frame buffer to work with. So somewhere I assumed that they would let us do the same. The frame buffer tag and the multiboot 2 header here. So what, we go to boot.s, and now we need to add the frame buffer tag. And here we have a short that's of type 5. Flags. What goes in flags? Does somebody tell me what the fuck flags is? Oh, here we go. If bit 0 flags, the bootloader may ignore this tag if it lacks relevant support. Sure. So I'll just put tags 0 for now, because I want to say don't fucking ignore me, please. And now I can go back to look for the frame buffer size one. So size is 20, which is a long. Oopsies, why am I saying dot flags here? This is short. Don't ignore me. Type 5, size 20. And here we have a 640 width by 480. And our depth, I think we don't care. I think you can just set depth 0. And 0 in a text mode. Value 0 indicates the OS image has no preference. Yeah, I have no preference. I do have a preference, but I'm pretending I don't because I think that's what we did before. No depth preference. Actually, I think I do. I can say 24, 8 bits per channel. Okay, and then I have to update my size. So my size is just plus 20, so 44. And now I think that we should get a screen initialized by the bootloader when we launch. Oops, we need to fix this frame buffer stuff. Unsupported tag 0x8. Alright. So I guess here I fucked something up. This is what? 2, 4, 8, 12, 16. Sorry, this is 2, 4, plus 4 is 8, plus 4 is 12, plus 4 is 16, plus 4 is 20. So size 20 is right here. So somewhere he thinks that he has a tag of 8. Probably this guy. So something's off. What doesn't he like? What doesn't he like? Unsupported tag 0x8. Very odd. Let's just change this 8 to a 10 here just to see if that was it. Invalid min, max, address, and or load size. So this was 24 before. And we have the terminator tag like this. Let's just put this back to the way it was. And I think that should boot again. Yeah, that's booting. So the question is why when I flip this around and add my 20 bytes for size to 44, why is this no longer working correctly? And it's very possible that I fucked something up here on the frame buffer thing. So what? We have short, short, long, 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 long. Type 5. Flag 0. What is this? If this tag is present, the console flag is set, blah, 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 blah. This tag specifies if the tag is present, bootloader assumes the payload has frame buffer support. Note that this is only a recommended mode by the OS image. Bootloader may choose a different mode if it sees fit. What am I missing? Maybe I bless my kernel and try to look for this multiboot header and make sure I'm not doing anything fucking stupid. So, what? Here's the header. So I have 4. Oh, man. Okay. Let's go through this one by one. So, here I have my header which is my magic, the architecture, the size. Checksum. Great. So then I have my type 5, length 20, I think. Yep, length 20. Oh, this was length 5 or type 5, flag 0, 20 bytes, 640. How do I validate this as 640? Oh, this is 480. Whoa, did I lose 640? Where did my 640 go? Am I high? Oh, it's here, 640. I see, the highlighting isn't doing it. So 640, 480. And 24 bits. And then my terminator tag is short 00. Whoa, 24. Oh, so here, this is my 1, 2, 3, 4, and then my 8, 4. Yeah, so I think everything's lined up the way I think it should be. I'm not seeing any, like, incorrect. As far as I understand the header, it's correct. Unless the checksum is wrong, but then that's a different, like, if the checksum was wrong, I wouldn't be saying the error I'm seeing, right? This is saying unsupported tag 0x8. And this is coming from Grub itself. So can I, like, what if I just, like, shove some extra shit on the end there? Still says unsupported tag 0x8. It really feels like it's this. If I just shove some more zeros on here, does it get confused? Okay. Okay, so that tells me something. So that tells me that it's giving me a 640 by 480 screen here now, I think. I think we can do like 1024 by 768. And we should see a bigger screen than we saw last time. Okay, cool. So our frame buffer is being initialized correctly. And there's something wrong with our terminator tag, actually. Or our size, maybe? Let's add these up again. So at the beginning, we have 4 plus 4 plus 4 plus 2 plus 2 plus 4 plus 4 plus 4 plus 4 plus 2 plus 2 plus 4. This does look wrong, eh? Let's double check that I add that up right. So we have magic plus architecture plus size plus checksum plus tag or type plus flags plus size plus width plus height plus depth plus tag plus flag plus size. No, that sure is fucking 44, man. Let's double check what the size thing is supposed to be. Header length is the length of the multiboot header in bytes, including the magic fields. What the fuck am I missing? And let's look at the terminator tag again. Lower, blah, okay, type is divided into 2 parts. Lower contains an identifier of contents of the rest of the tag. Size contains the size of the tag, including header fields. If bit zeros flags is set, the bootloader may ignore this tag. Tags are terminated by a tag of type 0 and a size of 8. 1, 2, 3, 4, 5, 6, 7, 8. Dude, I'm gonna lose my mind. What am I missing? Like, it doesn't make sense to me. Unless short isn't doing what I think, but it must be. It has to be, because this is working. But the fact that it's saying that it thinks that this is like type 8, what if I like... Oh, maybe here the size is supposed to be 40. Maybe the terminator tag isn't part of the header. Nope, it doesn't like that either. Does this matter at all? Like, does the size even matter? No. I wonder if this is lying to me. Maybe tags are terminated by type of size... by type of 0, size 0. Multiboot to terminator tag. Not working. Or maybe I can like Google the specific error I was getting, and maybe somebody else has fucking hit this because it feels wrong. Unsupported tag 0x8. Unsupported tag 0x8 multiboot grub. In contra... Oh, it expects tags to be aligned on multiples of 8 bytes. Aha. So here, I have to put every tag align 8. Aha. Aha, aha. Which means that probably, like, this size is probably wrong. I wonder if just setting the size to 0. That's pretty funny. If I just set the size to 0, Grub parses this correctly. Presumably because like that size field is kind of like just extra magic. So me setting size to 44 here is like technically wrong probably because of the alignment of the tags. So I think I'm just gonna, you know what, fuck it. I'm just gonna say set size to 0 because alignment makes size calculation tricky, and Grub doesn't seem to care that it's wrong anyways. Now, I know this is obviously incorrect, but I don't care because I'm only packaging my OS with this specific version of Grub 2. We can come back to this in the future if it's a problem, but I don't want to deal with it because I don't want to think about the alignment. All right. All right. So now we've like got a frame buffer initialized, and all we have to do is like parse the the data that came out of it. All right. All right. All right. All right. All right. All right. Let's do another checkpoint. What have we done here? Yeah, we'll git commit and say checkpoint multiboot, or what, 640 by 480 window without frame buffer parsing. All right. So what are we gonna do here? We're going to pull out the frame buffer info now that we got it. Which is going to be in here somewhere. Here. So here we're looking for type 8. So here we're going to say memory map turns into frame buffer info. Here we need to make a frame buffer info one. Here our frame buffer info. He's gonna have a what, tag? I guess we're gonna have our like internal and external representation. So frame buffer info priv. He has a type. He has a size. And then he has his shit. So what? We delete this, go to the beginning. That's pretty sick. Okay. So let's convert these all into what it said they are. Delete this shit off the end of the lines. Color info is God, stressful. So this is 1, 2, 3, 4, 5, 6 bytes. 1, 2, 3 bytes. We're going to assume that we have this version because I'm pretty sure this is what we have. So I'm just gonna say, screw it. We take this stuff and we make our vim macro again. So we go like this. Very good. So here, when we parse this stuff, this is gonna be like repr C. I don't know if this has to be packed, but we'll find out. This guy has to derive debug. This guy needs to write priv on the end. There we go. And then when we get the frame buffer info, we look for frame buffer info. We say that we make our for loop, pull this stuff out. Nope, never mind. This is fine. What do we do here? We look at the info. And we want to assert that, what is this? So frame buffer info priv. So I dot frame buffer type. We want to assert this is 1 for now. Otherwise, we've got the wrong RGB stuff in here. And can I just like print this for now? I think that we can kind of like arrange stuff in a way that this will work. If here, just after I initialize the kernel, I say let frame buffer is equal to, we have to make our multiboot 2 again. So multiboot 2 new with the magic and the info. We'll call get frame buffer info on it. And here we're gonna panic, but that's okay. I just want to see what happens. So failed to find mmap entries. This should be a frame buffer entry. So he fails to find it. Okay. That's interesting. On my tag iterator, let's print the type every time just to see. So here I do get a 6 in there. So shouldn't he return the frame buffer info? I do see a 6. Oh, he's panicking because I never returned the thing. That's fine. Print line hi mic. Let's see if we get a value out here. So how is he printing a 6, but he's never returning the frame buffer info tag? Oh, because 6 is memory map, 8 is frame buffer info. That would explain it. And I do never see an 8 in here. Okay, so what numbers do I see? Do I see a 7 for VBE? No. 5539 seems fucking broken. So that's concerning. That is definitely concerning. So it could be that our parsing here isn't working as we expect. So size is the location, add 4 as a const u32, dereference, and then align to 8. Maybe this is not supposed to be aligned to 8, maybe it's supposed to be aligned to 4. That doesn't look like right because that's just not running. Where if I align to 8, we at least get to this point. Is it possible that we're clobbering memory here during kernel init? Can we do this earlier? Maybe like after we initialize serial. We get the same thing. So either we're corrupting memory early or we're not seeing what we expect. Can I break? Maybe I run with GDB. And let's try to run, like we'll launch GDB. But we want to break at kernel main. Just right off rip. And look at info. And I think you can do like print the stuff at info and give me like 100 bytes of it. So here we're looking for anything that says 0x8. Which we're not seeing. Why the fuck not? Do we need to request? Maybe? Maybe we need to request that it tells us the frame buffer info, unlike in multiboot. Well, actually in multiboot 1, we did have to say, please give me the multiboot, the frame buffer stuff. So we'll read this a little closer. So, yep, this is just telling us where it is. Contain frame buffer dimensions, blah, blah, blah. If frame buffer type is set to 0, it means that it is X color. In this case, color info is blah, blah, blah. It says to 1, there's RGB color. If frame buffer type is set to 2, it means EGA text. Nothing in here does it tell us, it doesn't tell us like when it does or does not give this to us. Before we were seeing this like printing a tag of 5539, which seems sketchy as fuck. So maybe we'll look for that. I don't see that A3 anywhere in this dump of info. Maybe because 200 isn't enough. Let's think about this. So we have type 21, 1, 2. What are those? We have type equals 21. So that's image load. Type equals 1. Boot the command line. Okay. Type equals 2. Bootloader name. Type equals 10. which is the relocatable header tag. I guess we should also print, we should also print their sizes so that we can confirm as we're walking through these. We want to be able to confirm that they are sane, right? So here we'll say type is this and size is size. And we won't run with GDB this time, we'll just run it. Okay. So here we get to type equals 6. That could be long, and we know that that's right because it's giving us our like memory entries looked sane to us when we tested that. 10 has size 28, which is right. Type equals 2. Is a undefined size. Type equals 1. Also undefined size. But okay, so this type after the memory info is the one that looks sketchy to us. So size contains the size of the current entry, including this field itself. So it's possible that the size field for the memory map is not correct, and that's why we're having problems. Size contains the size of the current entry, including this field itself. It may be bigger than 24 bytes in future versions, but is guaranteed to be base adder is the starting physical. What the fuck? But is guaranteed. This isn't even like a full sentence. What the fuck? Okay, so let's look at, so the size here is 160. Which is clearly wrong, right? Because like that's where it starts to get fucked. So let's think. Maybe this is guaranteed to be a multiple of 8. It's currently set at 0. 1, 2, 3, 4. Let's look at, well, maybe we'll print the entry size. I just want to see, so print line map. Let's see what we get here. So we get type 6, size 160, entry size 24. So okay, calc. Here we should have what? 160 over 24 is 6.6, but we need to subtract some stuff. So we need to subtract this stuff. So 160 minus 4, 8, 12, 16. 160 minus 16 over 24 is 6. So there should be 6 entries. That seems reasonable, right? 6 entries, size 160, and we have to increment by 160, so then why is it fucked? Right, like something here is wrong. So we have location is a constituate. We increment it by size 8-byte aligned. Let's just do the stupid thing and see if 16-byte aligned is also correct. No, the 8-byte alignment is really lining up. And also, is 160 already 8-byte aligned? Yeah, it is. So why? Let's print the location and maybe we can see like what it's supposed to look like. If we like open in the shit. I think it's like this maybe. I want to see if we print the location after each one, after we've incremented, we can maybe take a look at if we're off by a little bit in this scenario, right? So here, after we print the memory map, we go to this address, and this address is where it all gets fucked. Okay, so now we can run with GDB, and we can try to poke that memory. So here I want to look at, I think it's this address. So I think I can say, what do I see for like 20 bytes here? And can I like subtract 8 maybe? Just to like look around this area. Okay, so what are we supposed to see here? We are supposed to see a type, a size, starting on each one, I think. 1, 2, 3, 4, 5, 6, 7, 8. So yeah, it does look just like fucked, eh? Where's the memory info one? The memory info starts here. So here we do see type 6, length 160, I think. A0, it's 160 probably. Yeah. So can I add 160? Yeah, and here I see type 9. Size really big. What is type 9? Elf symbols? Okay, wait. So that's reasonable. So when I add the 160 there, I get type 9, but that's not what I'm seeing here. I'm seeing type 5545. So why am I never seeing type 9? Is it possible that we're like overwriting memory at that location? Can I look at like my, how do I print the stack pointer? Maybe I'm like clobbering, oh, not Rust, GDB. It's the $. 1E, so we're far from 9A. But is it possible that 9A, like, is it possible that this is in the allocator region? How can we debug this? Let's print out the allocator range. Yeah, let's do that. So, can I, like, after we init the allocator, here we haven't initialized the logger yet or anything. Can I say, like, can I just make a function called, like, print ranges? And here somewhere we can look at our global allocator. Alloc, so we say alloc. Maybe we'll just like stash the whole range in here. So here we have struct allocator, and here we'll just punch in start and end, and we'll just stash those in here. Oh fuck, we can't. Oh, maybe we can start end. like this. And then here, when we initialize it, we just set the start and end. So, or we'll say start and size maybe. End is fine. So the big block. So we'll say alloc.start store, and we're gonna say big block with ordering relaxed. Big block is a memory map entry. So here we probably need like adder as const8. What doesn't he like? Cargo check. What doesn't he like? Oh, maybe as mutuate. Yeah. And end is the adder as mutuate add big block dot len as usize. Okay, now I can print the range. I can just say print line. We'll say the start is alloc.start load with ordering relaxed. The end is the end, and we'll say print line. We have this to this. And then here I just say once our thing is up, we can say allocator print range. And this should give us some clue as to if the areas that we're like reading the memory info from are like within the big block. So let's see. We are from 100,000 to like literally the end, and this is 900. So yeah, we're just in the memory allocated segment. We just like when we allocate, we just could overwrite it. So there's a good chance that we have overwritten our memory. Which means maybe what we should do is we should stash a copy of the memory info, whatever, and yeah, we'll just copy it to somewhere else, like immediately on entry. So kernel main here, we say what we say let size is, I think it's the first thing in there. I can't remember. Total size, yeah. So we say let what multiboot info size is this info dereferences U32. We say let info copy is fuck. I can't copy to somewhere without the allocator. I gotta think about this. Okay. I'm gonna think about this some more, but I think that we have a fairly good idea that at the very least, when we manually parse our multiboot info at the very start of our kernel main, but before we've done any shit, we get different results than if we parse it later, right? And because of that, we need to maybe like stash a copy of it, or make sure that we maybe reserve that section of memory so that the memory allocator doesn't overwrite that segment. But for now, I think I'm just going to call it there. I might come back to I'll probably come back to this tomorrow. Because yeah, I don't think I'm going to solve this in like the next 15 minutes, and I don't really want to stay on for much longer. So I think I'm going to call it there. We did get some like pretty good progress today. We did manage to like construct a multiboot 2 compliant kernel that initializes everything except the frame buffer so far, as our multiboot 1 version did, and we have like a pretty good path forward on how to get the multiboot 2 stuff. So yeah, thanks for watching. If you enjoyed what you saw, I stream most days at around like 1 or 2 o'clock Pacific time for like, 1.5 to 2 hours. And if you missed stuff, you can always catch up on YouTube, which is linked in the Twitch description. If you're on YouTube and you want to catch up on Twitch, feel free to, or you want to pop in and say hi on Twitch, feel free. Ooh, hold on. Before I go, Japfo is saying that he did look at the unsized type stuff. So I'm curious now. So here he throws in a repr_c struct that has some data that's a static reference. He converts this to unsized data. What is unsized data? This is this guy. Looks like the n-3 is really weird, but because casting to fat pointer to a slice to a fat pointer to the data retains the length of the fat pointer in data, this means that the total size of the data is the size of the size part of data plus the size of the fat pointer. So the correct behavior is subtract the size of size parts of data from the unsized size. Okay. So here I'm getting a pointer to data. Unsized data is const u8 as this. Oh, okay. I think that I was more wondering what happens on the other side, right? Because it was weird that like, here, can I like print line? Oh, you do have a debug data in here. Quick, cool, because that's what I want to see. Yeah, so the thing that bothers me about this is like, I'm not convinced that, this is the C representation. Right? Because like the fact that your debug like when you do a debug log of this, the fact that it stops, I think means that we've got a fat pointer in this data struct, right? Like here, if we look at print line core mem size of, I think it's size of val data. Oh, I probably have to do stood here because we're here. I think that we're not gonna get 3. Run. Why isn't this running? Am I missing something? Run. Why can't I run? Oh, it's compiling. 9. Right, like if this, what I wanted to see was Yeah, when I was talking about this earlier, I wanted to see like just like a thing that you could access at the end that didn't have a size associated with it. But if I look at like, yeah, here when I say size of val data, I'm getting 9, which means that this is 3 plus like, what is the extra 6? So like, where is that 6 bytes coming from? This should be data.thing. 6, yeah. So there's something weird going on where this like a slice at the end of the structure isn't like the 0 size thing that you get in C. So that's why I didn't do it that way earlier, because I was like concerned about this exact thing. And I'm sure that there's like a good reason or like a way to avoid this. I just don't know what it is. I wonder if you just like if you do like U8 0. Maybe you can do something like that and then like cast it away or something. Anyways, using a pointer was easier for me at that point. Got distracted. Anyways, thanks for watching, guys. Catch you on the next one. Yeah, I'll be back tomorrow, probably looking at the frame buffer stuff a little more with some fresh eyes. Thanks for watching. Bye.